Dr. Sabine Hossenfelder is a theoretical physicist, a research fellow at the Frankfurt Institute for Advanced Studies, and the author of the new book, Existential Physics, A Scientist's Guide to Life's Biggest Questions. Dr. Hossenfelder, welcome to the Climate Pod.
Hi, Ty. Good to see you.
Well, for those in the audience who haven't yet read the book, this first question might sound a little invasive, but we absolutely have to start here. Are you religious?
No, I'm not religious.
Well, of course, I ask you this because you ask each one of the physicists that you interviewed for the book the very same question first. So why did you ask these physicists if they were religious before asking them about anything related to physics?
I like to ask this question because a lot of the times physicists say, I'm not religious, but, and then comes the interesting part. So I could have continued my answer with, I'm not religious, but I do think that physics tells us a lot about those big existential questions that religion also addresses. And you see this in some of the answers that people give me in the book. I'm not religious, but I think there's something more to consciousness than physics can tell us. I'm not religious, but I think there are many open questions that science just can't say anything about, and we shouldn't dismiss religion, that kind of thing.
Well, how would you compare someone's quest to find a religion that provides an answer for everything to a physicist's quest to find the theory of everything?
Well, so this word theory of everything is being thrown around with a very vague meaning, really. Like, I think if you search for a theory of everything in terms of religion, it's actually a theory of everything, like life and making sense of life and the universe and so on. When we're talking about the theory of everything in the foundations of physics, we mean something a little more modest, something that brings together quantum mechanics with gravity and the other fundamental forces that we know of, like the nuclear forces and electromagnetism. So it's something rather specific. And the reason it's called the theory of everything is that for all we currently know, those four forces make up and describe everything we see, which may or may not be correct.
So why did you want to write the book, Existential Physics?
So I spend a lot of time on social media debunking science news headlines. You know, this is stuff like, we've made contact to a parallel universe, or physicists have created negative mass, or the quantum internet will allow us to send information faster than the speed of light. And normally my role is to say, no, we haven't, no, we can't, no, it's not possible. And I think that's important, but it's a very one-sided picture. It gives you this impression that physics just tells you what you can't do. And I wanted to say that there's more to physics. It also, it's inspirational. It tells you what is possible, and it makes you think about entirely new possibilities, really. Like if you know, I read a lot of fantasy, and it's quite interesting how many authors and also script writers draw on ideas that have come out of physics, like stuff like the multiverse and black holes, time can slow down, and wormholes, and all that kind of stuff. It's all physics.
Well, this book explores so many topics, none of which I could ever hope to fully comprehend. But I do want to ask you about a few of these topics that I do find particularly interesting. So let's start with an easy one. Can you explain how what we know about physics currently suggests that everything that's ever happened and everything that will ever happen is all happening at the same time?
Well, it's not so much that it's happening at the same time, but that the notion of now that we're so used to from our personal experience is meaningless. So it doesn't make any sense to say it's only this particular moment that exists. And this comes out of special relativity. Special relativity tells you basically, to make a long story short, it's impossible to give a meaning to the existence of now because different observers wouldn't agree on it. And who are we to say that one person's impression of what exists now is any better than some other ones? And the only logically consistent conclusion that you can draw from this is that all moments exists the same way. We're pretty sure that this is correct for what general relativity, Einstein's theory, and so on is concerned. Now, if you bring quantum mechanics into the mix, it gets a little bit more complicated because quantum mechanics has this indeterministic random element that whenever you look at something, it makes a jump, basically. And so it depends on how seriously you take this. Like there are some physicists who think that this is really the way the world works. And then there are others who think this can't really be the whole story. There is some underlying deterministic theory. And so quantum mechanics affects the future, because there could be those random events that happen. So, if you want to make a statement about whether the future already exists, it's not as clear in quantum mechanics as it is in Einstein's theory, but it doesn't change anything about the past. So according to Einstein, you could say the past actually does exist the same way that the present moment exists. About the future, there's this issue with quantum mechanics.
So how might someone apply the knowledge that there is nothing special about the now to some problem facing humanity today?
Oh, Jesus. To me, it's more like, kind of a spiritual, transcendental thing. Like we're basically part of this universe and we're just living out our story in it. So that's the way that I think about it. How you would actually practically apply it to some problem, I don't really think it has any practical applications. But at least for me, it has changed my perspective of how I think of our place in the universe. We're really just part of it, and it's all there.
Do you think that practical applicability is important to scientific research?
Well, certainly, but it doesn't have to be the case that everything is applicable. So special relativity and general relativity and quantum mechanics and so on, they all have applications. So there are lots of things that have come out of it. I mean, think of stuff like the images from the Webb telescope, right? I mean, so there are observations, and there's also lots of technology that has been developed along the way. So it's not that every little tiny insight you get from it actually has to be put to use somewhere. And I would also say, that those inspirational insights have a use in and by themselves because they're important to people and their understanding of themselves and the universe.
I really enjoyed the interviews that you conducted in the book. I talked a little bit about those interviews at the top of our conversation. In one such interview, the physicist, Dr. David Deutsch, told you that one can't predict the future growth of knowledge because no theory can be so good that it predicts the content of its successor. Do you agree with that statement?
Yeah, I agree with that.
So, are there certain principles then in physics that, if discovered in the future to be incomplete or untrue, would that drastically change the way that we perceive how the world works?
Well, that depends on what you believe about how the world works, but I think it's generally the case, as David points out, that there is an element to scientific discovery which you can't deduce from the knowledge that we already have. There's always this kind of inductive leap, so to say. You can't just say, okay, we know A, B, C, D, E, therefore F follows. That's not how it works.
Well, predictability is a theme that's found throughout the book. How does physics tell us that everything in our universe is predictable?
Well, it isn't actually. As I said, quantum mechanics has this random element to it. And there's also this issue, as you certainly know, that if you have a chaotic system, that may be theoretically deterministic if you knew the initial conditions arbitrarily precisely, but in reality you never do. So for practical purposes, you can't make a prediction beyond a certain period with a certain accuracy. So there are limits to what we can predict, and we know some of them, and for other cases we don't really know. Like, for example, what I find very interesting is that there's this big puzzle with the Navier-Stokes equation, where we don't really know if those solutions actually continue for all time. So if they just stop working basically and run in a kind of singularity after a finite period of time, which would actually be more non-predictable than chaos already is non-predictable.
Does human intervention in our ability to change the environment challenge the deterministic kind of principles of the universe?
Well, it depends strongly on what you think about consciousness. As I explain in my book, I mean, so I have a training as a particle physicist, and I actually do think that the brain is basically made of particles, and everything it does is in principle described by those theories of the fundamental constituents of nature, which in practice is completely useless, but in principle that's how it works. And then there's this small random element that comes from measurement processes. Now, people often find this talk about the measurement a little bit confusing, so I should probably add that what's a measurement in quantum mechanics doesn't necessarily include some kind of apparatus. It could just be an interaction with a big thing, which could be yourself. So in a certain sense, you're constantly measuring your own brain, and so it collapses, and it could have those random quantum jumps. They could be happening. And so it has this non-predictable element to it. And I've forgotten your question. Can you repeat this? Oh, and if human action brings in some, yeah. So for our practical purposes, human action is definitely very, very difficult to predict. And I guess you see this in climate models, right? If you're trying to make a prediction for what's going to happen, theoretically, you would have to take into account what policy decisions we're going to make, how technology develops, and so on and so forth, which we just can't.
Yeah, I mean, if policy makers do act on climate, it's going to be because scientists have studied the problem, they've raised public awareness, and they've determined the solution. All of this increasing everyone's knowledge of the climate crisis is basically what made them act. And if Dr. Deutsch is correct that future knowledge can't be predicted, then how can actions which depend on a certain level of knowledge, such as acting on climate change, ever be truly predictable?
Yeah, that's certainly right. Though I think the kind of knowledge that David has in mind is a kind of a breakthrough in the foundations of physics. You certainly know that he also mentioned this in the interview. He has this constructor theory that he's working on, and that would be a great breakthrough in the foundations of physics. But it would take a long time until it actually becomes relevant for policy. So I think, for what the next 100, 200 years are concerned, this is not something that we have to worry about a terrible lot. I mean, there's a general issue with this kind of prediction that depends on human action, which is that it becomes this kind of self-defeating prophecy, right? So if you say something bad is going to happen, you got to do something, and then people actually do it, then it doesn't happen, and they're like, look, it didn't happen, right?
Well, in the book, you also interview Dr. Zia Morali and talk about the possibility of humans creating a new universe. So is it possible? And if so, what would happen?
I actually do think it should be possible if our understanding of the beginning of our own universe is correct. And was very happy that I could get Zia to interview her and get her on the book, because I've talked about this before on my YouTube channel. And for me, this has been kind of an eye-opening experience, because people know me as someone who normally says, this is rubbish, don't believe it. And now in this case, I said, if you actually take it seriously, what we know about how the universe began, it came out of this quantum fluctuation of this field, and so on and so forth. Then one day we might be able to actually do it ourselves. There's nothing that stands in the way. Like, people think you need a lot of mass or energy to create a universe, but actually you can calculate it, and it's something like 10 kilograms. So it's not an unfeasible amount. And people were like, you can't be serious, right? They thought I was joking. And that made me think what I said earlier. I think I've painted a too one-sided picture. It's not that physics only says things are impossible. Every once in a while, it gives you this really big insight about something that you never thought would actually be possible, like possibly one day making a new universe.
You wrote in the book that an expanding universe can actually make its own energy. So how does that work?
Yeah, right. This is exactly why you don't need this huge amount of energy to, like, I think naively people have this impression you need all the mass and energy that's in all the stars and so on today. But the thing is that in an expanding universe, energy just isn't conserved. It's basically created out of nowhere. And as Einstein told us, energy is equivalent to mass. So you basically create mass out of nowhere. And I know this sounds completely crazy, because it disagrees with our everyday experience and everything we're told about saving energy and so on and so forth. So this really only works if you have an expanding space, and space is kind of expanding at the moment, but it's expanding very, very slowly. So at the present, it doesn't make any difference. For us, it's not an energy source that we can use. But in the early universe, this expansion would have happened so rapidly, it would have created an enormous amount of energy out of nothing.
Well, I don't get too many chances to talk to theoretical physicists, so please forgive me if this question sounds too much like science fiction. But like you said, if it's theoretically possible that humans could create a universe, and a universe, once it gets started, can create its own energy, is it possible then that humans could create universes and then extract their energy as a way to increase energy here in our own universe?
Well, at least for what we currently know about how this process would happen, the answer is no, unfortunately, because those universes would disconnect from ours. So it's like you create like kind of a small bubble, like a drop that forms from a water tap or something. But then at some point it gets too big and it pinches off and you can't reach it anymore. But then, this is all very speculative. It's based on our best current understanding of the theory. So God knows what people will be able to do in 100, 200 years or something.
Well, if that is theoretically possible, I mean, how do we know that our own universe wasn't created in a way to create energy for someone else's universe?
Yeah, exactly. I don't know. Big question.
Well, that's my only sci-fi question, I promise. You did mention that you are a fan of fiction. I assume that's science fiction. Do you think that that science fiction helps popularize physics and science in general?
It's certainly the case. And I actually got into physics by reading science fiction. I read a lot about space travel and hyperdrives and that kind of stuff. And I just wanted to know how much of this is really possible and how much of it is just fiction. And then I ended up reading lots of books about about physics, and so this is how it happens. And I generally think it's a good thing, for science communication, gets people interested in science. One has to be a little mindful to not conflate these two things. Like you don't want people to think that something which is actually fiction is science, right?
Yeah. Are there any pieces of science fiction that you think get the science particularly right, as well as the potential implications of the science?
I mean, there certainly historically there have been a lot of books from Jules Verne um, that have been very, very predictive about technological developments in the past century. And also, if you think about all the stuff with virtual reality or augmented reality, like this has been in in the science fiction literature like forever.
Well, one technology that's often found in science fiction is nuclear fusion. And that's been something that physicists have been working on for a long time. How close are we to creating an efficient nuclear fusion reactor?
Yeah, I'm afraid it's going to be a long time. I'll be happy if I see it in my lifetime. I'd say at least 30, 40 years or something like this. Don't get me wrong, I think it's really important that these experiments are being done and there's been a lot of progress, but it's also still a long, long way to go.
Why is that?
It's just a really difficult problem, and I think one of the major problems is that we don't really understand chaos. I think it's really, I mean, okay, so this is the theoretical physicist speaking, of course, but I really think it's a lack of mathematical understanding. And there's been a lot of progress in terms of chaos control, especially now with artificial intelligence, machine learning, and so on. There's a lot of things that you can do, but it only gets you so far. And I really think we need better mathematics to understand chaos and how to control it, and how to basically fine-tune the reactor so that the plasma stays where it's supposed to be and doesn't become unstable.
Well, in addition to being a writer, and you mentioned this already, but you've got this wildly popular YouTube channel, Science Without the Gobbledygook. What do you enjoy about creating YouTube videos about theoretical physics?
Well, for one thing, the videos that I do about physics, it's mostly stuff that I know already, and I enjoy sharing it with other people because I think it's exciting, and I just want them to also have a chance to get excited. But I don't only talk about my own research area. I also talk about other stuff. Every once in a while, I talk about climate models, but I also talk about renewable energies, nuclear fusion. I have one coming up about energy storage. I want to talk about cold fusion at some point. And I just find it interesting. You know, it's kind of like I have an excuse to look at the literature on all kinds of topics. And then when I think I kind of understand what's going on, not in any depth, right? I mean, I'm not going to become a fusion researcher by reading papers for 1 or 2 weeks. But when I think I kind of understand what's going on, I summarize it for other people, and I think people watch it just because it's useful for them. You know, I'm doing the work for them, basically.
Do you prefer educating people through videos more than other media?
Personally, I prefer writing. I have to say that one big stumbling point for me is just that, for better or worse, I ended up making this channel in English, which is for me is a second language, which gives me a lot of headache. You know, there are always words that I don't know how to pronounce, and then I have to figure out how they are pronounced, and then I made a mistake, and then I have to do it again, blah, 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 blah. So these are all problems I don't have to think about when I write. Which is easier, you know, from many points of view. But I also have to admit that it's a much more reduced medium, like especially when it comes to figures, animations. If you want to show what's going on, it's so much more powerful to do it with an animation and just put it next to you and say something like, in this animation you see blah 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 blah. It just works so much better.
You mentioned that you do videos on some climate science and renewable energy science. Is there any particular aspect of climate science that really intrigues you?
So I'm the kind of person who gets interested in pretty much everything. But one thing that I'm trying to do with my channel a little bit is something that I find is a shortcoming in the current coverage of climate models, is that we don't really talk about the problems. And this is a very big contrast to my own research area. Like, if you read anything about the foundations of physics, you basically only read about the problems, right? I mean, there's dark matter and we don't know what 85% of the mass in the universe is. There's dark energy and we don't know what this is either. We don't know how the universe began. We don't really understand all this stuff with quantum mechanics. We don't understand how to combine general relativity with quantum mechanics. So it's all about problems that we have. But when it comes to climate models, no one ever seems to talk about the shortcomings that those models still have. And as a scientist myself, this leaves me wanting, let me put it this way, because I know those models have shortcomings. I mean, I talk to climate scientists and then tell me about it, but it's like no one wants to write about it. And I think it'd be really, really important, especially when it comes to the big open questions, like the stuff with the tipping points, which I talked about in one of my video. This is the one where I was struggling to get out the Atlantic meridional overturning circulation. So this is one example. And then there's this story with the global stilling. Like, well, what's going to happen with the wind? Well, we don't really know. Like, I mean, this is my understanding of the situation. Like, I'm not a climate scientist. And I think that these big open questions, they are so important to communicate for people to be able to estimate the risk that they bring themselves in. Like, there's this big terrible thing that could happen and we have no idea what's going on because our models just aren't up to it. And so this is one of the reasons I'm talking about climate science.
Yeah, do you think, I mean, we've had so many climate scientists on this show. Do you think that the politicization of the climate crisis and climate science is the reason why climate scientists are a little hesitant to talk about potential flaws in their model? Because there's been so much misinformation about climate science. It's been peddled on purpose, right, by these industries that have profited and continue to profit off of climate inaction. Do you think it's that's causing climate scientists to be less forward about some of the potential holes in their climate models?
Yeah, I think that's definitely one of the main reasons. They're just afraid to talk about it because it'd be misinterpreted by people who don't have the most honest of intention. The other part, though, is that a lot of science writers who write about climate models actually don't know a terrible lot about climate science. So for them, it's much easier to stick with the official story. Like, the science is settled, we know it all, and so on and so forth. And then we don't have to explain what's actually going on with the wind. so it's just easier. But I think, like, this is a really dangerous thing to do, because we have to talk about the things that we don't know. And a lot of people who care about science, and I say this as a scientist myself, it makes me think this isn't quite honest. Like, there's something missing, and it makes me skeptical. Even though it's not that I mistrust the scientific literature, but if you have this mindset already that you think there has to be something wrong, then it just confirms your conviction that they're trying to hide something, right? So this makes me think we have to be more open about it and discuss those shortcomings. It's also, I mean, there's also a political aspect to it. Like, if you don't explain why you have to improve the model, it's not going to happen because no one thinks it's actually necessary.
So you wrote at the end of your book that you are motivated to make sense of your own existence. After studying physics for decades, do you feel that it has helped you make sense of your own existence?
Well, to some extent, yes, and to to another extent, no. I think I've come to realize that physics is really good at telling you about some things and not about others. Like if you're trying to use physics to learn more about humans, complete failure, right? It doesn't tell you anything. And it's something I know this must sound crazy, which to some extent I believe, because when I was a student, there was all this talk about self-organized complexity and that kind of stuff, which is very physicsy. To some extent, and there's this sociophysics, I think it's what it's called, if you use physical principles to describe how society works and that kind of stuff. And of course, this still exists, and it explains some things, but it gets you only so far. But physics is really good for sorting out some of those confusions that we have about time, for example, which we started our conversation with. How much can we actually learn about time? What can we conclude from our observations? So it's this deductive aspect that physics is really, really good at.
Well, if you're interested in knowing how the universe began and how it's going to end, or whether or not there is a multiverse, or if human consciousness can be uploaded to the cloud where we're going to be able to live virtually forever, check out Dr. Hossenfelder's new book, Existential Physics. Even for somebody who, like me, who obviously knows nothing about theoretical physics, I found the book to be fascinating, so I highly recommend it to anybody seeking answers to the biggest questions in the universe. Dr. Sabine Hossenfelder, thank you again for joining the Climate Pod.
Thanks for having me.